Hi girls, we're going to start with our notes with section 5.3, this binomial distribution. Hopefully you can see everything okay. And your notes are a little bit out of order, I realized when I was going through them this morning, so you're going to have to kind of sort through them. The first page is fine. And we only have one vocab, it's just the binomial experiment, and that is just a probability experiment that satisfies 4 different requirements. And I went ahead and wrote the requirements out for you in your notes. So the first one is that there has to be a fixed number of trials. So we have to say we're going to flip a coin 4 times. And so our fixed number of trials is 4. And then each trial can only have 2 outcomes. Well, that's perfect because if we flip a coin, there's only 2 outcomes that we can have. We can either have a heads or a tails. And then number 3, the outcomes of each trial must be independent of each other. And that works fine with tossing a coin because it doesn't matter what happens each time you toss a coin. It doesn't make a difference for the next time you do it. Number 4, the probability of success remains the same for each trial, and the probability of success for tossing a coin and getting the heads remains the same or is consistent each time you do it. So that would be a appropriate example for a binomial experiment. All right, so those are the 4 requirements, and your probability experiment, if it meets those 4 requirements, then it's a binomial experiment. So the next part is the outcomes of a binomial experiment, and the corresponding probabilities of these outcomes are called a binomial distribution. So all of our outcomes of that experiment and the corresponding probabilities is that binomial distribution. So that's what you have to fill in there. The next portion of the notes is just your symbols and what those symbols mean. So those are things that you need to be able to recognize and remember. So the symbol of the probability of success is P of S. The probability of the fail is P of F. The numerical probability of success is the lowercase cursive p. The numerical probability of failure is the cursive q, and the number of trials is n, and the number of success is x. The last portion just tells you some more notes about the binomial distribution. Your x should be greater than or equal to 0 and less than or equal to n. Your x can start with 0 and go all the way up to n. The probability of success equals your p, and the probability of your failures will be 1 minus that p, which equals q. Okay, so nothing major there. So now let's actually go ahead and start looking at these new formulas. So the next page that you should have, and I'm not quite sure if that's the next page in your notes, is this formula with the box at the top. And I just left that box there so you can go ahead and put your formula in. And it's just this n factorial over the quantity n minus x factorial times x factorial times p to the x times q to the n minus x. So I know I already lost some of you, you're over it because there's a lot there. But once we start doing this, you're going to see how easy it is to plug all that in. It just seems like a lot right now. So for our first example, I wanted you to see how we were doing things and how we can start doing things now because of this formula. So our first example is about a coin. We're tossing it 3 times, and we have to find the probability of getting exactly 2 heads. So this is just like last week's stuff when we were doing those probability trees on the board. So I did a fake probability tree. So I just wrote down all of my outcomes. So I did, heads, 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 tails, and I just went through all of the options that I could get for tossing my coin 3 times. So when I did that, I found that out of there was 8 total options, and when I'm getting exactly 2 heads, it happened 3 times. So here, here, and here. So that was 3 out of 8, which is 0.375. And then I thought, well, I better check and make sure it meets all my 4 requirements to know that it is actually a binomial experiment. So was there a fixed amount of trials? Yes, there was exactly 3. Were there, let's see, only 2 outcomes? Yes, you can only have heads or tails if I flip the coin. Were the outcomes independent? Yes, the first outcome did not depend on the second did depend on the first or the third, and so on. And then was the probability of success consistent? Yes, my probability of success was 1/2 from the first to the third trial. So they all of my requirements are met. So it was definitely a binomial experiment. And now I want to show you that because it's a binomial experiment, you could use that formula that we talked about at the top of the page. So I'm going to show you how you could do that. So using that formula, we needed to list all of our symbols. So our n was 3, our x was 2, our p is 1/2, and our q is 1/2. And where did I get this? Well, my n was 3. How many times was I going to toss my coin? 3 times. How many? Exactly 2 heads. That's what I was looking for. So that's why my x is 2. Probability of success was 1/2, and my probability of failure was 1/2. So now I just used those variables and plugged into my formula. So the probability of getting 2 heads is 3 factorial over 3 minus 2 factorial times 2 factorial times 1/2 raised to the second power times 1/2 to the 2 minus 1. So when I plugged all of that in, I got 3 over 8, and which is 0.375. So same answer. So I just want to show you that you could do it 2 ways. It's just that if I was doing this, tossing into coins 6 times, I'm going to have a relatively bigger probability tree, which is going to take me a lot more time. Okay, so that's using this new formula and finding out my variables to do so. So now here's where I think that our confusion gets into play with our notes. So I need you to go to example 2, which I think is out of order for you guys. Example 2 is about a survey that 1 out of 5 Americans say he or she has visited a doctor in a given month. And if 10 people are selected at random, find the probability that exactly 3 will have visited a doctor in the last month. Okay, so we're going to find out the probability that exactly 3. So I'm going to fill in my variables. My n is 10 because I have 10 people selected. My x is 3 because I'm concerned about exactly 3 people being at the doctor's. My probability of success says, well, it's 1 out of 5. Up here we said that 1 out of 5 Americans do visit the doctor or have visited a doctor in any given month. My probability of failing, the Q is 4 out of 5. All I did was 1 minus 1/5. Okay, so now I can plug all this into my formula and then solve. So my probability of exactly 3 is 10 factorial over 10 minus 3 factorial times the 3 factorial times 1/5 to cubed times 4/5 to the 10 minus 3. I plug all that in and get 0.201. Okay, so again, nothing too terrible. I was able to plug that in using that formula and solve. So now I am going to go out of order, and I'm going to go to back to that other page to example 3. And it doesn't say example 3, it just says example, and it's about a survey that found 30% of teen consumers receive spending money from part-time jobs. And then it says, well, if 5 are randomly selected, find the probability that at least 3 will have a part-time job. So now the reason I'm going to this example is because the last one said exactly 3. Now we want to find at least 3. So that means we're going to have to do that formula a couple of times. If I'm going to find out how many have at least 3, I'm going to have to find out the probability of 3, the probability of 4, and then the probability of 5, and then add those all together. And that's what I did here for you, so you can see how I plugged in and solved. And then when I found the probabilities of all 3 of those, I added those together and got my answer. You can pause that and go through how I plugged in. I won't bore you with talking you through that. But I just wanted you to see, this ends up getting a little bit tedious if you're doing, how about if you had 10 people and you needed to find out at least 3, you would keep doing this for probability 6, probability 7. It would get very tedious. So what's nice is there's a table you can use. So instead of having to use this formula, you can go to the table and find that information. That table is on page 638 in your book. And I think that it's Appendix C and it's Table B. So that is going to be very helpful. And I want to go through this next question with you and show you how to use the table. So the next question I'm going to go over in your book, and it's about that tossing the coins one. And the tossing the coins, remember our N was 3, our X was 2 because we did 3 trials, and our X was 2 because we had we wanted to find out how many times we would get heads exactly twice, And then the probability of success was 0.5, and the probability of failure was 0.5 as well. And remember, we found our value to be 0.375. We did first the fake tree diagram, and then we did the actual formula. And now I want to show you that if you would go to that table in the back, all you're going to do is you're going to look, well, my n was 3, so I'm going to have to go on the left-hand side and scroll down until I find the 3. And then I'm going to have to use the corresponding x value. Well, my x value is 2, so I'm at 3 and then 2. And then I just follow the corresponding p-value. And remember, my probability of success was 0.5. So I go down to that and over, and my answer is 0.375. So you just need to practice using that table. And I want you guys to go ahead and try to do that. Now remember, this is all in your book. I'm just on page 281 in your book. Remember, that table is Appendix C, Table B. It's a table, and it's on page 638. And then I want you to practice this page 285, numbers 4, A through C, and 5 through 7. See what you can do. And then tomorrow we'll finish up these notes, and I'll go over any questions that you might have. So keep me posted. Let me know if you have any questions, and hope you guys are doing well. Talk to you soon.